sometimes if we have a function we want to work with, but it's not particularly easy to work with, it's not particularly easy to perform algebra or calculus on, we can replace it with a function that's equivalent and easier to operate on. So that's what we learned back in 9.1, that if I have a power series, if I have specifically a geometric series, and I have my ratio that's in between -1 and 1, I can write an infinitely long series, a polynomial with infinitely many terms, and it's equivalent to this rational function 1 over 1 minus x. And I found out that I can do any kind of algebra I want as long as I do it to both sides of my equation, and I can make polynomials that are equal to kind of like pretty strange functions that would otherwise be difficult to compute with. So it turns out to be a very useful thing to have if I want to compute with a difficult function, especially if I want to perform calculus on it, because it's very easy to perform calculus on a polynomial and tough to perform calculus on some other functions, especially if I need to write a program, like a computer program, to calculate. I can't sit down and try to think of U substitutions. I have to have like a very systematic method that I could use, and that's easy to write for a polynomial. So if that's such a great technique, what am I going to do when the function I want to approximate isn't anything like 1 over 1 minus x or one of its transformations? So this is the topic for 9.2, is what's another way you could write an infinitely long polynomial, maybe infinitely long, to approximate a function that's not polynomial. It turns out our best bet is really an extension of what we did back in chapter 4 of writing a tangent line approximation to a function. A tangent line approximation has a value that matches at some place. So at one particular x value, I have the exact same function value, and then has the same first derivative, so the same slope. You should imagine extending that idea. I'm going to write now a function that has a polynomial that has the same function value, has the same slope, so same first derivative, has the same second derivative, so same concavity, I guess is one way to think about it, same third derivative, fourth derivative, fifth derivative, and I can take that out as far as I need to for whatever my purpose is. So I think in class you worked on this warm-up of constructing a polynomial that has it's degree 4, because it has an x to the 4th term in it, and it had these behaviors. So you practice taking the derivative, and you notice that since we were evaluating the polynomial at 0, most of the terms would cancel out, and you could figure out a1, a2, a3, and a4. And I think when I left you, most of you were working on trying to start this guy. So this is in your textbook, it's in your notes. I'll show you a little PowerPoint to kind of get you started if you had trouble getting started. And it's going to lead us to a technique that we can use every time. So this one example, I didn't give you any hints. I'll show you some hints now, but just notice that that's our goal of trying to discover a pattern that's going to work for us every time. So if I want to have a polynomial function, 4th degree, that's sort of an arbitrary number, so it has an x to the 4th term in it. It would look like this, a little bit like that warm-up, except I want this polynomial to approximate f of x's natural log of x. So I'm going to, can I figure out what a sub 0 would be? Well, it's going to have to be the same as natural log of 0. So that's going to be how I start. The function I'm trying to approximate is natural log of x plus 1. I need f of 0 to match exactly, well, I need my p of 0 to match exactly my f of 0. So here's f of 0, that's natural log of 1, which is 0, and p of 0. You can imagine plugging in 0 for all the x's, right? P of 0 is just going to be a sub 0, so if f of 0 is 0, I'm going to need my a sub 0 to also equal 0. I'm going to keep this process going, but it's going to involve taking the derivative of the natural log of x plus 1 function several times. But you can kind of walk through here. You can use this to check your work. Remember, this example is also in your textbook. we got here? You see any patterns emerging? Okay, so once I find my A0, A1, A2, A3, and A4, and kind of collect them all together and write my P of X polynomial. So, I could call it a function, I could call it a polynomial. It's not an infinite series because I've decided to chop it off at 4 terms. So we're going to talk a little bit later. It's a big topic for the next section about how good your answer is and how do you decide what error there might be on your answer. Okay, so here we go. And then just, that's interesting, so check out how that simplifies. 0 plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So that's a pattern that we're going to notice. And you can see when we plot those, if the same way a tangent line approximation was only good near the point of tangency, I can only guarantee that this is called the Taylor Polynomial approximation. We'll learn more about the official language in a minute. I will only guarantee that it's really an excellent fit near the point of tangency. So we call that the center. But wow, look at this. If you zoom in on that, look how close those two functions are, as long as you stay pretty close to 0. Okay, so this is what we want to come down to. We want to notice sort of that pattern that happened. And this is going to hold. I think it's on your paper. We'll look at your paper in a second. So f of 0 over 0 factorial plus f prime of 0 over 1 factorial plus f double prime, so second derivative of f of 0, f prime of 0 over 1 times x. F double prime of 0 over 2 factorial, so second derivative over 2 factorial times x squared. So you're noticing 2, 2, 2, 3, 3, 3. That makes this pattern pretty easy to remember, and that's what we need to know to write our very first, on our own, Taylor polynomial. Okay, so I'm going to switch back to your handout. Alright, so I'm pretty sure the official title for 9.2 is Taylor Polynomials. Now, notice that a Taylor series or a Taylor polynomial, if you're going to have the center be 0, so if that original point of tangency be at x equals 0, we also call that a Maclaurin series or a Maclaurin polynomial. I don't know the history there. But this is always going to be true. If you want a function to have derivatives of if you want a function to approximate like a polynomial function to approximate some more complicated function, and as long as the derivatives of the function that you're trying to approximate exist on some interval that has 0 as the center, then you can write a series in this form. F of 0 plus the first derivative of 0 times x to the first plus the second derivative of 0 over 2 factorial times x to the second. You can see these numbers show up again. So 1 divided by 1 factorial, 2, 2, 2. This would be the third derivative of f of 0 over 3 factorial times x to the third. So those numbers all match, which makes this pretty easy to remember. And if you used infinitely many terms, you could write that summation. You're going to go from term 0 all the way up to the infinite term of f, the kth derivative of f at 0 over k factorial x to the k. If you're centering at 0, so these are all zeros, these are zeros, these are zeros. Again, this is called a Maclaurin series. And if you decide that you don't want infinitely many terms, you're going to chop off your polynomial after some number of terms that we're going to talk about how to make a good decision later on the AP test. They'll typically tell you, write a fourth degree or write one with 3 terms. Then you would just stop after n terms. That's called the Taylor polynomial of order n. Okay, so go back up to the top for a second. So this is pretty cool because now I can write a polynomial approximation of a function that isn't even close to being polynomial. So imagine the cosine function. That long summation that you just saw, I can use that pattern to write a polynomial function that approximates cosine. So the example on your page says we should write the 6th order polynomial approximation of the cosine function. So what am I going to need? I'm going to need to know cosine, and it says at or about x equals 0. I'm going to need to know cosine of 0, which you knew before you ever met me. I'm going to need to know the first 6 derivatives of the cosine function. I'm going to need to evaluate those derivatives at x equals 0. Well, the super cool thing about cosine, after you take the derivative 4 times, you're back at the beginning and you just take the same 4 derivatives over. So you could write this out. You'll come to probably remember this one by heart, I hope. So if f of x is cosine of x, I know f of 0 is 1. That's going to be my point of tangency, right? So the point that's sort of I want to draw write my tangent line approximation to, except now it's not a tangent line approximation. It's like a super amazing polynomial approximation. But I know it's going to have that ordered pair, 0, 1 on it. I'm going to go through and find the first, second, third, and fourth derivatives of cosine. So first, second, third, and fourth derivative of cosine. And for each of those, I need to evaluate the derivative at x equals 0. Because remember, I'm going to need the first derivative of f at 0, the second derivative of f at 0, the third derivative of f at 0. Okay, so I've got these, and they're just listed here. And remember what the box on your paper says. I can write a polynomial by writing f of 0 plus f prime of 0 over 1 factorial times x to the first, plus the second derivative of f at 0 over 2 factorial times x to the second. And I'm just going to start writing that pattern. I was asked to write it out to the 6th order. I think this slide goes further. Look at that. Okay, so I'm going to start writing. This is f of 1 plus f prime of 0 is 0. So the coefficient that's going to multiply my x to the first term happens to be 0. I've got my second derivative evaluated at 0 is negative 1. So that's why I have a negative 1 times my x squared factor divided by 2 factorial. My x to the third factor is going to get divided by 3 factorial, but that third derivative evaluated at 0 is 0. So this is cool for cosine, and you'll see soon for sine. Every other term is odd, as 0. Okay, so there we go. How far do I need to go? So 6th order means, whoops, I should have kept this guy in. 6th order means it comes from finding the 6th derivative. So this is my term that had the 6th derivative in it. Notice I didn't write in the 5th derivative and the 6th derivative, but that's because I got back to cosine and sort of my sequence starts over from the top. The 5th derivative, negative sine, 6th derivative, negative cosine. But to be frank, this is the coolest thing that happens in high school calculus. So we know a tangent line approximation can be pretty good, like right at that point of tangency. So we don't call it the point of tangency anymore. We're going to call it the center. Here I have a center at x equals 0. Watch how good this polynomial approximation is to cosine. So that's one term, I would just have this constant function, y equals 1. With 2 terms, look at that. With 3 terms, so this yellow highlighting up here gives you an idea of how many terms in the polynomial are getting used. The red is the actual cosine function, and the blue is my polynomial approximation. So check this out. That's 4 terms. That's 5 terms. That's 6 terms. Look, those match so closely you can't even tell them apart until like the very end over here. Okay, so, and check this out. It looks like I don't have a small interval of convergence. My approximation is getting better and better, like further and further out. So that's something to notice about our Taylor polynomial approximation for cosine, is that I don't have a limited interval of convergence anymore, and the more and more terms I add, the more that interval grows.